double click பண்ணலாம் இல்லையா fill up பண்ணல Okay, so welcome to the online class of CSE 419, the numerical linear algebra or mathematics 4. And so last time when we have the face-to-face lectures on Monday, we talked about elementary permutation matrices, and then we see how the elementary permutation matrix operates when you pre-multiply a given matrix A by an elementary permutation matrix. We see that it basically interchange two rows of a matrix, the matrix multiplication by elementary permutation matrix. So, and then I wrote a theorem which says that if A is an n-crossed matrix, then there exists a certain elementary permutation matrices P1R1 up to Pn minus 1 Rn minus 1, and the elementary lower triangular matrices L1 M1 up to Ln minus 1 Mn minus 1, which we defined in the previous theorem as well, such that when you multiply all of them in that order, we get an upper triangular matrix. So this is where we left, right? Right, so we wanted to show that this elementary lower triangular matrix multiplied by elementary permutation matrix, lower triangular matrix and elementary permutation matrix give you an upper triangular matrix, right? So what we want to show is, we want to show the existence of elementary permutation matrices and elementary lower triangular matrices. Right? So we have to start uh, by finding the elementary lower triangular matrix as well as the elementary permutation matrix. போர்டு நான் எழுதுறது தலையில இல்லை அவங்களுக்கு இது தெரியுது அவங்களுக்கும் தலையில தான் தெரியுமோ அல்லது ப்ராப்பரா தெரியுமோ இது தெரியல இங்கே தெரியும் Thanks. Right. So I hope now you are able to see it in the proper line, right? So earlier it was switch back and forth. So now you probably have the proper view of the what I am writing. So now you want to prove this by mathematical induction because that is what we did. So in order to do that, we write the matrix A as a column wise, right? As a column wise matrix notation, right? So we are AI is the ith column of A, right? So you name the first column as A1, second column as A2, third column as A3, and so on. Right? So you know that you first want to eliminate elements below the diagonal on the first column. So if the first column is all zero, then you don't need to do anything, right? So that is the first case. If A1 is zero, right, then you can choose both the element permutation matrix and the elementary lower triangular matrix as identity matrix, right? So you don't need to do anything, so you can choose them as identity matrix, right? So now if that is not true, right, so else you know that if the column is not zero, then at least you will have one non-zero element, right? So then you can find that non-zero element and pick that and multiply by a permutation matrix such that the first component is non-zero, right? So L, there exists R1 which is greater or equal to 1 such that ER1 transpose E1 is non-zero. So you will have at least one non-zero component in the column. So you pick the non-zero column. So that suppose that non-zero component is on the R1 place, then you can pick that. So once you pick that, right, so you can choose the elementary permutation matrix. Right, so when you multiply by elementary permutation matrix, right? So by the first column multiplied by the elementary permutation matrix and its first component is non-zero, right? So you are, if A is zero, the first column is all zero, you don't need to do anything. So you can just pick the permutation matrix and the lower triangular matrix as identity matrix. If not, there will at least be one non-zero element. So you can pick that non-zero element. Suppose it is on the R1 place, then you can pick that R1 place and find the elementary permutation matrix with interchange first row and the R1 row of the matrix. So then P1 R1 times A1, which is the first column, has first component non-zero. Right? So this is enough to find the elementary lower triangular matrix, right? So if this is true, right? Right. So if this is true, then you know there exists an elementary lower triangular matrix, because in the earlier theorem you know that as long as you have non-zero diagonal term, you can always find the elementary lower triangular matrix, which we did last time, right? So we see how we can find the elementary lower triangular matrix. So here we use the elementary permutation to make non-zero term on the diagonal. So now we can find there exists an elementary lower triangular matrix, right? And so there exists elementary lower triangular matrix such that A1 is a matrix, right, which is L1 M1 into P1 R1A. So again column notation. So I'm going to use A1, A2 1 and AN 1. Right? So you have the new matrix when you multiply A by elementary permutation matrix first and then elementary lower triangular matrix. Right? So the construction of elementary lower triangular matrix I am skipping here because I did that already in my previous theorem. So it is the same mechanism. So but here but after this multiplication, we know in the first column every component below the diagonal on the first column are 0. Right? So for all j running from 2 to n, Ej transpose A1 1 will be 0. So that is how we do complete the first step. Right? So we prove actually the first step. Now for induction purpose, let us assume that the result is true for some k steps, and then we will prove it for the k plus first step. Okay, so for induction purpose, we assume there exists L1, M1 up to LK, MK, and we assume there exists P1, R1 up to PK, RK, such that AK is equal to LK, MK, PK, RK, all the way up to L1, M1, P1, R1, A. Let us name that as A1, K, A2, K, up to AN, K. Right, so let us assume that there exists elementary permutation matrices and elementary lower triangular matrices up to first k steps, such that you get a matrix, right, which has 0 below the diagonals on the first k column, right? So here, right, so where you can see and for the first k columns, every component below the diagonal are 0. Right? For all j greater than I, so those are the components below the diagonal. Right? J is equal to I is a diagonal term. So j greater than I gives you all terms below the diagonal. So, and for the first k columns, we say that this one is true. So now we have to show that it is working for the k plus first step. Right. So if you want to show that it is working for the k plus first step, right, we know that right now if the k plus first column has all zeros below the diagonal, then you don't need to do anything at the k plus first step, right? Because it is already in the upper triangular pattern. So if the k plus first column of this matrix, right, has all zero below the diagonal, then you don't need to do anything. So in that case, like what we did in the first step, right, then we choose both Tk plus 1 and Lk plus 1 as identity matrices. So basically you don't need to interchange any rows, or you don't need to do any elimination. So in that case we choose the element determination matrix and element lower triangular matrices as identity matrices. Else we have to go to the elimination as well as the row transformation. Else we know that there exists else we know that there exists a place below the diagonal on the k plus first column which is non-zero. There exists a term on that column below the diagonal which is non-zero. So as long as it is non-zero, you can always find a corresponding element permutation matrix that interchange the k plus first row with the row rk plus 1. So Okay, so then so in that case, we know that, right? Sorry. And so we will have a non-zero term on the diagonal of the certain column vector, right? Or the k plus first column of A, right? Because by element permutation matrix, you can always bring that non-zero term towards diagonal. So then clearly, right, again according to last theorem, which I did earlier, right, there exists an elementary lower triangular matrix, right, such that, right, so you will have a matrix AK plus 1, you denote it as by a matrix AK plus 1, which is a multiplication of LK plus 1 and K plus 1 with the elementary permutation matrix you find here, PK plus 1, RK plus 1 with AK, which is the previous matrix you have after doing K steps of elimination. So here again, we name this as columns, right? So A1, K plus 1, all the way to AN, K plus 1. And so you will have rename that matrix in terms of columns as A1 K plus 1 up to AN K plus 1. Right? So here, right, so we know that EJ transpose AI K plus 1 will be 0 for all j greater than I, and I running from 1 to up to K plus 1. Right? Because it's all, because we already know how to choose this elementary lower triangular matrix from a previous year. Right? So then obviously that will take care of the elimination part on the K plus first column. Right? So that's how we do the K plus first step. Right? So obviously, you know, you did for first step, and then you assume it is true for K plus first step, and then you show it. So you assume for K step, and then you show it works for the K plus first step. Right? So then obviously, by mathematical induction, you can see that the theorem we try to prove is true for all n. Okay, so now I'm going to do an example of Gaussian elimination with this row interchange. Right? So let's say A is 1 1 1 1, Okay, so you want to convert this matrix A into an upper triangular matrix by multiplying suitable elementary permutation matrix and elementary lower triangular matrix, right? So obviously you know, first step here, you don't have to do any row interchanges, right? So obviously you know P1 R1, you can choose that as identity matrix, right? And then you know you can choose your M1, right? Like the way we did in the previous example, 0, 1, 1, and 1, right? So 0, 1, 1, and 1. So clearly, right? So this clearly, right? So when you multiply by identity matrix, this does not change, right? So this does not change. And then for this M1, when you multiply by elementary permutation matrix, you know what happens. This row minus this row minus 1 times this row, and this row minus 1 times that row, right? So that is what you have. So clearly, you can simply write it down 1, 1, 1, 1, and 0, 0, 1, 1, 0, 1, 2, 2, and 0, 1, 2, 3. Right, so this is your A1. According to theorem, this is my A1. Now I have to go to the second step, because this completes my first step. Now I will go to the second step. Right, so if I want to go to the second step, then the next step thing is I have to look for the diagonal term on the second column. So clearly my diagonal term here is 0. So obviously you know I have to interchange that row with some other row. Right? So that point is 0. So I cannot do the elimination. So I want to interchange the row. So I have the luxury of interchanging any two rows. Right? Either I can change this or I can change this. Right? So any row you can choose. So I will choose the third row. Right, so I will interchange second row and third row. So I choose P23. Okay, so P23 times E1. Okay, so this means the first row does not change. Third row becomes the second row. So 0, 1, 2, 2, 0, 0, 1, 1, and 0, 1, 2, 3. Right, so first I interchange the row number 2 and row number 3 in A1. Right. So once I do that, then I will look for the elimination part. So I need to find an M2. Okay, so my M2, clearly I have 0, 0. Like first two terms are 0, 0. And then my M2 is this divided by diagonal. So 0 divided by diagonal, that is 0 again. Right. So for your information, let me write 0 over 1. And then here, again 1. Right, because 1 over 1. So now if you multiply this by elementary permutation, elementary lower triangular matrix, Right? So when I multiply this whole thing by elementary lower triangular matrix associated with this N2, I know my first two rows does not change. So 1, 1, 1, 1, 0, 1, 2, 2. Third row I multiply by 0, so again no change. So 0, 0, 1, 1. And then the last row minus the first row. Sorry, last row minus the second row. 0, 0, 2 minus 2 is 0, 3 minus 2 is 1. Okay? So now I can stop here because I already have upper triangular matrix. Right? So I don't need to go for the next step because I already have elimination here in the second step already. So I have upper triangular matrix. Then I have no, I don't need to go to the next step in elimination. So this is how you do elimination with pivoting, right? So row interchangement is called pivoting. Okay? So whenever required, you have to multiply by elementary permutation matrix. Otherwise, you can always choose your elementary permutation matrix as identity. So that is how this process works. So we call this as a Gaussian elimination with pivoting. Right? So that is a name which is applied for this kind of approach. But so here we see that we do multiply by elementary permutation matrix whenever we have a zero on the diagonal term. So that is one issue we have in Gaussian elimination, right? Because when we have 0 on the diagonal term, so clearly we cannot divide by 0, so we have to interchange the row. Right? There is another case where you may need to do a row interchanging, right, in order to get a better results in Gaussian elimination. Right? So we will do that as a remark here. Okay, so as a remark, right? So this process is called Gaussian elimination with pivoting. Right? So that is how we call it. Right? That's a first remark. Second remark is, right? So we may need to do it, right? right? So you may need to do the elimination, right? So row transformation or row swap whenever the diagonal term is very small compared to the other terms below the diagonal. Right? So that is one peculiar case where you may need to do a row interchangement, right? So that is the pivoting technique or multiplying by elementary permutation matrix, and that is required whenever the diagonal term is very small compared to the other term. So we will see an example how this thing works, right? So this second remark part works by looking at an example, right? So we will start with this example, right? So very simple one, 0.0001 x1. Right, so let us consider a system of equations which look like this: 0.0001 x1 plus 0.0002 x2 is equal to 2. So you try to do this without interchanging the rows and with interchanging the rows. Right. So first step is okay. So first step, and so first we will try to do without row swap. Right. So then clearly you know that you don't need to go for a row swap, so you have to multiply by a elementary row triangular matrix and do the row interchange, right? So here is your system, 0.0001, right? And then 1, 1 and 1, x1, x2 is equal to 1, 2. Right? So you try to do without row interchanging, right? So you know your m1 is equal to 0, 1 over 0.0001. Right, so this is how you choose your m, right? So clearly, right, so you can easily see that L1, M1, so this is your matrix A, X is equal to B is your system, right? So you know L1, M1, A will look like 0.00011, and then this will be 0 minus, right, and 1 minus 1 over 0.0001, right? At the same time, we will try to evaluate B as well, right? So on the other side, I am going to write L1 m1 times b is clearly 1, 2 minus 1 over 0.0001. Right, so you know how to solve by multiplying element in lower triangular matrix. So I'm not going to show all the work. Right, so this is how you're going to have the system. Right, so when you solve this, you will end up with x2 is approximately equal to 1, so x1 is approximately equal to 0. Right, so that is what you are going to get. But that is not a correct solution because you obviously know that if you put x1 and x2 are 0, here you get 1 is equal to 2. That is not true. So this is not a correct solution. Right, so without row interchange, if you solve this by just Gaussian elimination, you notice that you get a solution which is not correct. Now, if you apply row interchange, right, so if you apply row interchange, first thing you do is you multiply by P21, right, of A, right, so that is clearly 1, 1, 0.0001, 1, right. So when you multiply left hand side, you multiply the right hand side as well. So P21 times B, you get 2 comma. So now you apply Gaussian elimination, right. Right. Now if you apply Gaussian elimination, in this case your m1 is going to be 0 and here 0.0001 divided by 1. Right, so this time your m is going to be, after interchanging the rows, after multiplying by elementary permutation matrix, you get 1, 0.0001. So your m1 is going to be this. Right? So then you know L1, m1 into P21A will look like this: 1, 1, and 0, and 1 minus 0.0001, and L1, M1, P2 and B will look like 2 and 1 minus 0.0001. Right, so when you interchange rows, you get this system. Again, this is an upper triangular system. Without interchanging rows also, you get an upper triangular system. But without interchanging the rows, you get a solution x2 is equal to 1 and x1 is equal to 0, which is not correct. But this will give you x2 is equal to 1 and x1 is equal to 1. Right, so obviously you can see this is a correct answer. So this is another usage of row interchanging in elimination methods, right? Not just because we have 0 on the diagonal, even if the term on the diagonal is smaller than the elementary, the off diagonal terms, right? So the term on the diagonal is very small than the term below the diagonal on any step, right? Then also it is advisable to do a row interchanging to avoid getting into a wrong answer, right? So that is what we mentioned in the remark, and this is an example of how you can avoid going into the wrong answer by doing a row interchange. So before we finish, I'm just going to mention you about factorization. Like two different factorizations we are going to talk about here. So first thing is, okay, so first thing is, first thing is PA is equal to LU factorization, right? So this type of factorization, because earlier we have a factorization called A is equal to LU factorization, right? So here, because we have elementary permutation matrices as well, right? So we will have PA is equal to LU factorization, right? So recall. Right, so this is what we have, right? So we have, when we have a matrix A, and we can find elementary permutation matrices P1 R1, and then elementary lower triangular matrix L1 M1, and so up to Pn minus 1 Rn minus 1, up to elementary lower triangular matrix Ln minus 1 Rn minus 1, and when you multiply all of them in front of A, you get an upper triangular matrix, right? So from this, right, we want to get to a factorization like this. Okay. So what are the difficulties we are having in going from here to here? Okay. The first difficulty is you have permutation and lower triangular, permutation, lower triangular, permutation, lower triangular. All of them are mixed inside each other. So permutation matrix, and then lower triangular matrix, then again permutation matrix, again lower triangular matrix, and that is how the theorem is written. So we have to see whether we can rearrange this, and whether we can move the permutation matrix into other side of a lower triangular matrix. So we will try to see, right, as an exercise. Right, so as an exercise, I'm going to ask you to see whether Pij times Lk Mk, right? So this is a permutation matrix, elementary permutation matrix in front of a elementary lower triangular matrix, and here it is an elementary permutation matrix, and it is behind the elementary lower triangular matrix. Right? So I want you to check whether this one is true. Right? So you notice that when you move the elementary permutation matrix to the other side of the elementary lower triangular matrix, so you can see that this vector is changed. Here I have mk, but here I have nk. So it is changed, but you can see that the length of the vector is not changed. It is k and it is still k. So you have first k terms 0. Like you know that if it is m1, you have first term 0. m2, you have second term 0. First and second term 0. So if it is mk, you have first k term 0. Similarly, nk, the first k term 0. Right? But the numbers are different, right? So the numbers might be interchange between them. Right? So that is how this goes. So I will leave this as a homework and I will give you the hints of how to do this, right? So you know that the Pij times Lk Mk is basically Pij times I minus Mk into Ek transpose, right? So that is how you define the elementary lower triangular matrix, right? So at the very beginning, I define elementary lower triangular matrix LIM as I minus Mi Ei transpose. So here Mk Ek, so I have this, right? So now you have to work it out and see whether this can be written as I minus Nk Ek transpose into Pij, right? So whether you can work all the way down here is the question. So that's something I leave for you as a homework, right? So we will do this exercise if you are not done. We have some other time, right? But here I will leave that as an exercise. And if this is true, then we can work this thing out, right? If this is true, then right, so by this exercise you can see that, right? So you take this elementary permutation matrix and move behind, move behind, move behind, and move it here. So in other words, you take this elementary lower triangular matrix and move in front, move in front, and move in front, right? Okay, so if you move this L1, M1 in front of this, so here you obviously know you will have a P2, R2. This is what you have. So when you move this M1 is not M1 anymore. It will be changed to some other value. But still the length is same, but it will be changed. And then you move one more step, and you move one more step. Right? So eventually, after moving everything together, here you don't need to do anything with this because this is already in front. And so you just move the other terms. And basically, you push L1, L2 up to Ln minus 2 in front, in front, in front, in front. So you have all the L's together and P's together and U together. Right? So you do this because of what you have as this exercise. Right? As long as the results in this exercise is true, you can do that. And so once you do that, then the rest is easy. Right? So then it's just moving the things together. Right? So N1 Rn minus 1 up to P1 R1 A is equal to L1 minus N1 up to Ln minus 1 minus Mn 1 u. Right, so you multiply by the inverse of these matrices on this side. So clearly you know this one is L, U, and here you have A, and now you have a product of elementary permutation matrix, right? So you have to show that a product of elementary permutation matrix is a permutation matrix. That is not a big thing because that is obvious, right? So here you have, right? So where if we have only one row operation, we call it elementary permutation matrix. Right? So if you have many row operations, then we call it as a permutation matrix only. Right? So that is how you do this procedure. And so this is about factorizing A as PA is equal to LU. So there is another type of factorization as well. So that is again for a special type of matrix, right? Not just for the matrix A. The next factorization is for a special type of matrix, right? So we are going to see that factorization as well. Right, so here we are going to talk about factorization of a symmetric matrix. Right? So here we call the matrix is symmetric, right? So we call a matrix is symmetric if A transpose is A. Right? So when you transpose the matrix, you still get the matrix A itself. So in this case, suppose A has a factorization A is equal to LU. Right? So you know L is a unit lower triangular matrix and U is an upper triangular matrix. Right? So that's something we studied on the first year. Right? So suppose A is equal to LU, but you know A transpose is equal to A. So LU transpose is equal to LU. Right? So this is what you have in LU factorization, right? So you say LU factorization, right? So if A is LU, then A transpose is A, so LU transpose is equal to LU. Okay. So clearly you know that U transpose L transpose is equal to LU, right? So L is a lower triangular matrix, so L transpose is an upper triangular matrix. You know that. And U is an upper triangular matrix, so U transpose is a lower triangular matrix. So what I am going to do now is I am going to combine the lower triangular matrix together and upper triangular matrix together. Right? So So I move this L here, so I get L inverse. I keep U transpose, and then I move this L transpose here, so I get L minus transpose. Right, so now what I have is L is a lower triangular matrix, L inverse is lower triangular, U is upper triangular, so U transpose is lower triangular. So this is, and this is upper triangle. Okay? So I have the lower triangular matrix is equal to an upper triangular matrix. Right? The lower triangular matrix is equal to upper triangular matrix. So that can be possible only in one scenario, and that is whenever the matrix is a diagonal matrix, right? Because you know upper triangular matrix diagonal and above the diagonal terms, lower triangular matrix diagonal and below the diagonal terms, right? So clearly the only way that these two are equal is whenever they are diagonal. Right, so where D is a diagonal matrix, right? So this is only possible whenever D is a diagonal matrix, right? So then if you combine these two, right, so you can see that D times L transpose is U. Right? So when you combine these two, you get D times L transpose is U. Right, so you have D times L transpose is U, right? So now what we have is, so originally you have A is equal to LU, right? But because A is symmetric, you get to a point where U is equal to D times L transpose. So now you have L, D, L transpose. So you have, instead of upper triangular matrix, you have a lower triangular matrix, diagonal matrix, and the transpose of a unit lower triangular matrix, right? So here unit lower triangular and D is a diagonal term. Right? So D is a diagonal matrix. So this is a special type of factorization. And so this can be a special type of factorization. Right. So now again I am going to write the rest as an exercise for you to think about, and we will think about it in the next class again, right? So now right, so if A is a real matrix, then A transpose is a symmetric verse. But if A is a complex matrix, then symmetric is not enough. So you have to go for conjugated transpose. So in that case, we call it Hermitian. Right? So we call this matrix as Hermitian matrix if A Hermitian is equal to A. And A Hermitian is the conjugate of A and transpose. At the very first class, I introduced you about conjugate and the transpose. Right? So in this case, again I am going to write this as an exercise with this definition. If A is Q times Q Hermitian, right? So if A is a Hermitian matrix, that is, it satisfies this condition, right? And if A can be written as LU factorization, for real matrix I show you. If A is symmetric, right? If A is equal to A transpose, then you can write A as L transpose. So half of the work is already done. Right? So now you have to think of this conjugate part only. Right? So if A is Hermitian, then you can write A as Q times Q Hermitian, where Q is a lower triangular matrix. Okay? So this I leave as an exercise for you to think about and come back to the next class. So we will continue from this exercise in the next class, and this Hermitian thing is where the next chapter is begin with, right? So here we talk about Hermitian matrix. So we will complete this exercise in the next class, which is very simple. I hope you all should be able to do it, and we will complete this part, and then we will start doing some elimination by using this Hermitian type of matrices, right? So that we will see in the next Monday class. We will continue online lectures until further notice, right? So the online lectures will be held on the regular, according to the regular timetable. We will have the online lectures that will be scheduled by the computer department. Right? So we will see this the rest of the section on Monday at our regular time.